Hi, folks. Today we're going to talk about Euclidean geometry. Now, Euclidean geometry is very old school. So Euclidean geometry refers to the geometric structures studied and formalized by Euclid back in 400 BC in Alexandria. His primary works, the Elements, which introduced what we now call Euclidean geometry, it's been in publication ever since it came out. And it's still used to teach geometry in some places. Many of the math topics in the Elements already existed, but what Euclid did was he formalized the idea of plane and solid geometry and expanded on it. And he really gave a blueprint for how we should approach developing and exploring mathematical topics. It was very big, and it still is. I mean, mathematicians aspire to do what Euclid did with the elements for other mathematical fields. And only in the last century have folks really been able to go and do that. And so let's talk about the structure of geometry and what makes it so that we've been using this approach to studying geometry for 2,000 years. And so what he did is he created an axiomatic approach. And so what made Euclid's approach to geometry so unique was that he found a set of base properties and used these properties to develop and analyze all geometric objects. These base properties are called postulates or axioms. And they are unproven statements which we treat as true to explore various mathematical structures. Sometimes we explore what happens when we don't have all five. In particular, hyperbolic geometry says, what if we only have the first four? And if we just focus on the first one, we get graph theory. And so we often say these are unproven statements which we assume true. Sometimes we assume they're false and figure out what happens then. And so the axioms of Euclid. Euclid used 5 axioms to build his geometry, and we will go through all 5 of them. The first 4, they're pretty solid. We assume those for most things when we're talking about geometric objects. The 5th one, sometimes we say we don't want to deal with this one. The 5th one is called the parallel postulate, and we'll explore what happens when that one goes awry. Essentially, you get geometry on the surface of a sphere or geometry on the surface of a Pringle, which can be fun to explore. Let's start with axiom 1. And so axiom 1 says a straight line may be drawn between any 2 points. And, that seems reasonable. But this gives us the idea of points and a line. And so now we have the idea of points. And so points are some object or something on a surface. And we can draw a line between them. This may be in 2 dimensions, this may be in 3 dimensions, but we now have a way of visualizing what a line actually means. Any terminated straight line may be extended indefinitely. That's axiom 2. And so now we've gone from the idea of a line segment to a line itself, something which goes on infinitely in both directions. It raises the question of what if we only wanted to go in one direction? Well, in that case, we would call it a ray. And we can do mathematics involving rays. Often when we're talking about angles, we're focused on the idea of rays. Axiom 3 introduces a circle as well as the idea of measure. And so a circle may be drawn with any given point as center and any given radius. This radius is the idea of a measure from a center to the outside bit. And it's the first time we really talk about being able to replicate some measure. And so we now have the idea of circles and a way to measure distances using the radius. Axiom 4, all right angles are equal. And so now we have the idea of an angle. And so an angle is a way to measure the spread of a pair of rays. And in this, we're defining a right angle. Well, in our modern jargon, we could say a right angle is 90 degrees. But in Euclid's case, he was referencing the angles of a square or something like that. And so we can see that all of these different right angles are equal. The fifth one's interesting. And so if two straight lines in a plane are met by another line, and if the sum of the internal angles on one side is less than two right angles, then the straight line will meet if extended sufficiently on the side on which the sum of the angles is less than two right angles. What this is saying that if we have two line segments which are meeting in a particular way, they're either going to be parallel or they're going to cross. Now, this is true on the plane. Either they're going to be parallel or they're going to cross at some point, and we can determine where they are going to cross. If we are dealing with lines on a sphere, this isn't actually going to be the case. And so that's where axiom 5, we sometimes get rid of it when we're dealing with other types of geometry. And so while these are the axioms of Euclid, we often explore what happens when we remove one of these axioms. When we remove the parallel postulate, we end up with the geometry of curved surfaces. If we only play with axiom 1, that's what graph theory is about. And there are other geometric structures to explore, but Euclidean geometry is the easiest to visualize. When we think of all of the shapes and all of the structures from geometry which we know, they all come from these 5 axioms. Every triangle, square, rectangle, circle, we can even go into 3-dimensional objects. It's all coming from these 5 axioms. And so these are very powerful axioms. And if you want to go and explore all of the ways in which you can get everything from those 5 axioms, you might have to take a real geometry class or go and purchase the elements. It's still available. Planar and solid shapes. Let's talk about the types of shapes we can analyze using our axioms. And so to begin with, we have planar shapes. And so a planar shape is a 2-dimensional shape on a plane. Generally, these shapes can be constructed using a compass and straight edge, and we frequently have formulas to determine the area and perimeter of the shapes. The shapes we'll explore will be circles and polygons. And so we're going to focus on a simpler version, but there are others like ellipses, or we could get an egg shape or other things. A triangle, that's an easy one. Hopefully we all know what a triangle is. A triangle is a 3-sided shape. We can classify it based on the number of sides and angles and determine what they are when they are the same. We have scalene triangles where nothing's really the same. Isosceles is where 2 sides are the same. And equilateral is where 3 sides and angles are the same. We can also say a right triangle has 1 right angle. An obtuse triangle has 1 obtuse angle, meaning 1 angle which is greater than 90 degrees. And an acute triangle has 3 angles which are all acute. We can find the area of these using a formula, 1/2 base times the height. It's fun to actually go and figure out how to get that formula, though. And for all of the geometric formulas, you can go and prove all of these formulas. And it's a good exercise to go and figure out the formulas and where the formulas come from and how you can get them. And so we won't go in depth into showing them here. You should probably go and try that on your own. The Pythagorean theorem, for instance, this is one of the oldest provable theorems. It existed in ancient Egypt and Babylon and probably predates that. I mean, this is some ancient mathematics that people have known. Given a right triangle with legs A, B, and C as the side opposite the right angle, it'll always be true that A squared plus B squared is equal to C squared. Always, always, always. There are many, many proofs for this. And if there's something which satisfies this equation, A squared plus B squared equals C squared, we call that a Pythagorean triple. We also use this as the Euclidean norm when we're talking about measure, and we'll talk about that at a later date. Quadrilateral has 4 sides. We have rectangles, parallelograms, trapezoids or trapeziums, depending on where you live, squares, rhombuses, and kites. There's a general quadrilateral, doesn't have to have anything in common. Yeah, and if 2 sides are parallel, we can find the area by multiplying the base times the height. If it doesn't have 2 sides which are parallel, you might have to break it into triangles and figure out the area that way. For regular polygons, that's polygons which have the same side length and equal angles all around. And so we have an equilateral triangle, a square, a pentagon, a hexagon, a heptagon, an octagon, a nonagon, a decagon, and we can just keep on going. A lot of different names for them all. In general, if you need to find the area, you're just going to break it down into triangles. If you want to find the perimeter, just add up all the sides. Circles are interesting. So a circle is the collection of all points a fixed distance away from a given point. If you do not know what a circle is, it's the round one. The distance around is called the circumference. The distance across the center is called the diameter. The distance from the center to the edge is called the radius. And this is where we get the number pi popping up. And so the number pi is used to represent the ratio of the circumference to the diameter. Turns out the circumference divided by the diameter is always going to be the same number. And that's what pi is. It's roughly 3.14, but it's an irrational number which goes on forever and ever and ever and never repeats. We have formulas for area, circumference. You can prove those if you want. I might recommend trying it. We also have this idea of pi versus tau. The last 15, 20 years or so, people have started to wonder if maybe we're using the wrong circle constant. And so pi is the measure of a circumference divided by the diameter. And we've been using that for a few hundred years or so. But tau might be a better circle constant. Essentially, when we're talking about tau, we're saying that one revolution is equal to 1 tau. It's measured as the, the circumference divided by the radius instead of the circumference divided by the diameter. And using tau, if we are going halfway around the circle, well, we're going half of tau. We're going a quarter of the way around the circle, it's a quarter of tau. If we were dealing with pi, well, halfway around the circle would be pi. A quarter of the way around the circle would be pi over 2. And so in many ways, tau is nicer, but pi is just so standardized that it's not likely to change. And so I'll leave it to you as to whether or not you like tau better or pi better. Another big topic when we're talking about Euclidean shapes is the Platonic solids. And so the Platonic solids are 3D shapes which have regular polygons for the faces. They're named for Plato, who hypothesized that these solids represented the elements. Whether they are representing the elements or not, I will leave that to you. But we have the tetrahedron, which has 4 triangles and represented fire. We have the hexahedron, also known as the cube, which has 6 squares. It represented earth. The octahedron, which had 8 triangles, that would be this one here. It was representing air. We have the dodecahedron. That was my favorite always. It has 12 pentagons, and it represented ether. Think of it kind of like spirit or something. And then there's the icosahedron, which is 20 triangles, another fun one, and it represents water. If you've ever played with magnet tiles, you can make most of these. Dodecahedron might be a little tricky. Other geometric solids, I mean, there's a lot. As soon as you start putting different shapes together or start measuring things in terms of distances, you can get things like spheres and cylinders and cones. And there are formulas for finding the volume and surface area of all of them. All of those formulas you can actually prove yourself. They're not too tricky to prove. But yeah, volume is the measure of the amount of space an object takes up. Surface area is you add up the areas of all of the surfaces, all of the faces of the region, then that's what the surface area is. Let's now talk about congruence. And so geometric congruence is similar to congruence in other forms that we've talked about. And we'll soon see why that is. And so traditionally, one of the first places we discuss congruence is as related to shapes. We say that two shapes are congruent if they have the same shape, and so the same side lengths, the same corresponding angles. They can be in different locations, they can be rotated or flipped, and still be congruent. They just have to have the same sides and the same angles. The symbol for congruence is the equal with the little tilde on top. And what's special about congruence? Well, it's an equivalence relation. And so all of the rules for equality that we have so far for numbers and sets and all of that, it applies for geometric objects as well. And so we can quickly prove that congruence is an equivalence relation. Reflexivity, a shape is always congruent to itself. Symmetry, if shape A is congruent to shape B, then shape B is congruent to shape A. And we also have transitivity. If shape A is congruent to shape B and shape B is congruent to shape C, then shape A is congruent to shape C. And so this idea of congruence defines an equivalence relation. And the equivalence classes would just be whatever the shapes are. And so every unique shape is in its own equivalence class. We also have the idea of similar shapes. And so two shapes are similar if they have the same angles and their side lengths are proportional. Similar means the shapes have the same structure, but they may be different sizes. And so they could be scaled up or scaled down. If you look over here, these two hearts, they're similar because they have the same shape, but they're different scale. Over here, the basketballs would be congruent, and they're also similar. Similar is or if something is congruent, it's automatically similar. Here's the thing, similarity is also an equivalence relation. And so if we think of the three rules, we have reflexivity, symmetry, and transitivity. Well, if two things are similar, something is similar to itself, because if it's the same item, then it's similar to itself. Transitivity, let's see. Oh, symmetry, I forgot symmetry. Symmetry, if one thing is similar to another, then that other one is similar to it. And transitivity, if we have three things that are similar, then they're all similar to one another. And so similarity is an equivalence relation. One of the main things we focus on in geometry, as it's typically taught, is the idea of congruence of triangles. And so when we're thinking about congruence of triangles, if we know certain information about the angles or the side lengths, we can determine if triangles are similar or congruent. If you know all three sides, you can determine congruence. If you know all three angles, you can determine similarity. And if you know some information about the sides and some information about the angles, you can sometimes figure out congruence or similarity. And so that's how we can play with congruence of triangles. Again, if you want to figure out all of the details, you can take a real geometry course. Ooh, next up we have constructions. This is one of the big parts of geometry. So what can be made with a compass and straight edge? Because of the axioms, Euclidean geometry is often thought of as the geometry of compass and straight edge. We can form line segments using a straight edge. We can form circles and measure things using a compass. Of note, protractors, which measure angles, would not be allowed for constructions. We also don't have rulers. I mean, we can use a radius to kind of create a ruler, but not in the same sense as the Cartesian coordinate system. Well, maybe it's a little complicated there. It then becomes a question of what structures can we analyze by constructing them with these tools? And so what kinds of things can we make using a compass and straight edge? Well, one thing we can make is a perpendicular bisector. And so we can make a line segment which is perpendicular to some other line segment. And that's what we can see here. So we have one line segment here. We have another line segment here. We can construct this basically by putting a compass with one end at the B and then curving around here, and then do the same thing on the other side and curve around here. And where those 2 points meet, if we draw a line through them, we are going to get right angles. In a standard geometry course, you actually go through this. You create this type of perpendicular bisector using a compass and straight edge. Another popular one is an angle bisector. And so we can create an angle bisector, which is dividing an angle in half. We start by using an arc, using the compass. And then from those 2 places where the arc crosses our angle or our 2 rays, we're then going to have 2 additional arcs come out. Where those arcs cross, if we connect the corner here, the angle B, to this value, we will have divided the angle evenly in half. And so that's an angle bisector. Those are just 2 examples. There are a lot of constructions that you can create. And in a standard geometry course, you will create dozens upon dozens of different constructions and see if you can determine things which are parallel or perpendicular based on your constructions. And so parallel and perpendicular lines can be constructed wherever we need. We can also easily construct certain angles, such as a 45 degree, a 30 degree, a 15 degree, or any combination. We can construct any arc or line segment, but there's still a number of things that you can't really construct. And so at this point, it becomes a question of what is the most difficult things for us to construct? One very complicated thing is regular polygons. And so some regular polygons are constructible while others are not. The Greeks did not know which ones you could do and which ones you couldn't do. And so for the Greeks, they knew you could do 3, you knew you could do 4-sided, and they knew you could do 5-sided objects. And you could do any multiple of 2, 3, 4, or any multiples of 2 for objects of length, or objects of with 3 sides, 4 sides, and 5 sides. And so if you wanted to create a 10-sided object, they knew how to do it. If you wanted to create a 20-sided object or a 6-sided object, they knew how to do it. But what about others? Well, Gauss came up with a proof for a 17-sided object back in 1796. And this was really the first big advancement for Euclidean geometry in like 2,000 years. And so it was kind of a big deal. In addition to this 17-sided object that he made, he also showed which sides it's possible to make and which polygons it's not possible to make. And so you can construct a 17-sided polygon, but he was able to prove that a 7 or 9-sided polygon are not possible. And again, that's kind of a big deal. How do you prove something like that? Well, this was the first big advancement in Euclidean geometry in a long time. There are some other things which are impossible. So the 7-sided polygon and the 9-sided polygon, we proved that that's not possible. Here's a couple others that are really big and are classical problems from Euclidean geometry. Trisecting an angle. And so we know that we can bisect an angle, which means split it into 2 equal parts. Is it possible for a given angle to be divided into 3 equal parts? Well, for certain angles, it's possible, but in general, it's impossible using just a compass and straight edge. You can use a protractor to approximate, but you're not going to be able to trisect an angle in general. Another one is squaring the circle. And so given a circle, is it possible to construct a square which has the exact same area as that circle? This would be very useful because it would give us a geometric way to calculate pi, but it's not possible. It's not possible to do via constructions using compass and straight edge, at least. And so this was a problem which people were trying to figure out for a very long time with no luck. Final thoughts? Well, Euclid's geometry has served as a fundamental pillar of mathematics for over 2,000 years. And with good reason. It demonstrated that an area of math can be formalized. It can be broken into its base parts and explored fully. That's what Euclid did. He figured out what geometry actually is at its basest level. And then he was able to explore the entirety of the field based on those fundamental principles. These days, mathematicians focus on other areas of geometry, but they're ultimately just extensions of the work that Euclid did. And so we'll soon be exploring some of those other branches of geometry, but it all goes back to Euclid, trying to understand how those axioms developed the entirety of geometry. With that, I'll let you get to work exploring where you find geometry in the real world. Good luck, folks.